This is the third lecture in Unit 9, Momentum and Impulse. Here we're going to look at the connection between Newton's laws of motion and momentum. First thing we should do is review Newton's 3 laws of motion. So there's this guy named Newton. He's really smart. One day he has a great idea. This video is actually not about the probably apocryphal story of the apple hitting him on the head, ultimately leading to his law of universal gravitation. Instead, we're going to look at his 3 laws of motion, the first of which tells us that things have inertia, or more often it's stated as thus. Objects in motion stay in motion, and objects at rest stay at rest unless acted upon by a non-zero external force. The second law tells us that if there is an unbalanced external force, which we call sigma f, or the sum of forces, that's equal to an object's mass times its acceleration. So really, these are the same law, right? Because if you have a 0 sigma f, or no net force, you have no acceleration, and therefore your velocity is constant. In other words, your inertia takes over. You tend to stay in motion or at rest, depending on what you were doing to start with. Third law tells us that objects that exert forces on each other always receive the same magnitude of force in return. You've often probably heard this phrased as, for every action there's an equal and opposite reaction. I don't love that phrasing. It's probably better to say, for every force there is an equal and opposite force, or better yet, every time we touch, the force is equal. Starting from Newton's second law of motion, we can rewrite this to have a better understanding of how it relates to the idea of momentum. And Newton was aware of this as well. He actually used the equation we're about to derive more often than the one you see here. So starting from sigma f equals ma, what is acceleration? Well, that's the instantaneous rate of change of velocity with respect to time, or the derivative of velocity with respect to time, dv dt. So I'm just going to replace the a in Newton's second law here with the expression dv dt. And now that we have this expression, you notice we have a really interesting numerator. mdv can be rewritten as d, or the instantaneous change in the quantity mv. Why did I do that? Because the quantity mv we know to be momentum, or p. We can also extend this to move the d out in front of the p, so the instantaneous change in mv is the instantaneous change in momentum, dp. And now I can take this expression, instantaneous change in momentum, or dp, and substitute it up here in the numerator, giving me my final equation, sum of forces equals dp dt, or we could state that as net force is the time derivative of momentum. So let's try to connect this to Newton's third law, which tells us that for every force there is an equal and opposite force. Well, if you're in an isolated system, that means that there are no external net forces, or if there are, they're all balanced. So your only net forces are between the objects in the system, which are internal forces, and therefore do not cause the system center of mass to accelerate. In other words, we can rewrite Newton's third law in terms of momentum thusly. For every impulse, there exists an equal and opposite impulse. Again, this is all contingent upon the assumption that we're only talking about isolated systems, or systems in which the momentum is conserved. But when that's the case, if you push me and I push you back with the same force, we will experience the same change in momentum.